All right, welcome back, calculus students. In this video, we're going to be talking about net signed area and total area, which are two different concepts. The last time we approximated area under the curve, there was a specification that the function had to be positive, because when you actually do this integration, area under the curve for a negative function, you're going to get a negative value. So the Riemann sum becomes the area of the rectangles above the x-axis minus the area below. And this is what we're going to call our net area. So let's take a look at an example of a function that goes above and below the x-axis. Oops, still orange. I don't like that. And that's going to be f of x equals 2x from -3 all the way to +3. So our first point would be -3, -6. Our final point would be 3, +6, and it goes through 0, 0. So as you can see, we have area under the curve down here. And we have area under the curve up here. And what happens is these areas are actually going to cancel out and equal 0 because we have the same area on both sides. So what happens when we find our area is we're going to do an area under the curve here. Sorry, those are poorly drawn. And we're going to do an area under the curve over here. And what's going to happen is those areas are going to be equal and opposite. And so when we go to find this area, it's actually going to be 0. So to find this one, if we're writing it in notation, we're just doing from -3 to 3 of 2x dx, and we're going to turn it into a Riemann sum. So we've got I equals 1 to n, and then we've got our delta x, which is 6 over n. It actually doesn't ask us to do this as a Riemann sum, and so I don't have a right and left defined, which means I don't have a great way to define this function, but I'm just going to assume left-hand sum in this case, which is not how I actually drew a right-hand sum on one side and a left-hand sum on the other. Don't do that. But we're just going to let this be 2 times x, and we're going to let x be 6i over n. So that's your partition width times I, letting I be each individual interval. But because these are right triangles, we can just use the area formula. A equals BH. And so we've got, in this specific example, we've got a base of 3, a height of 6, and then we've got another base of 3 and another base of 6. And so that gives us a net signed area of 0. And we want to compare that to be the total area. I'm not sure when we define total area. Okay, so it's over there. But the total area under this curve, we just kind of understand that one of these is negative, and so we apply an extra negative, and we would end up adding these areas together. So we would get, what is this, 9 plus 9? And find that our total area under the curve is actually 18. So total area and net area. So for the next example, we're going to do x minus 2 from 0 to 6. So it's going to start here at -2. And then by the time we're at 6, we're actually up to +4. So I'm going to count by 4. 1, 2, 3, 4, 5, 6. Draw a point. Connect the dots. It's going to cross the x-axis at exactly 2. And so I have a cute little triangle down here. And that's going to be subtracted from the area of the triangle up here. So let's calculate each of these areas. For the above axis triangle, we are looking at a base of 4 and a height of 4. And for the below axis, we're looking at a base of 2 and a height of 2. So our net signed area is 4 times 4 over 2 minus 2 times 2 over 2. And that's going to give us 8 minus 2, or a net signed area of 6. Let's talk about the properties of definite integrals. So our main properties are sum and difference and constant multiple, and they're pretty much exactly the way you would expect them to be based on your knowledge of limits and derivatives and the same properties in those contexts. So there are a few properties that are unique to integrals, and that's first one is that the integral from a to b of f of x dx is equal to the negative integral from b to a of f of x dx. And as well as this idea that you can break an integral into two bounded parts, which is actually how we're going to find our total area. So let's just split this next example using the definite integral as the sum of three definite integrals. And so we're going to do -2 to 1 of the first term of 3x cubed plus -2 to 1 of 2x. Oh, each of these have their own dx. Hang on. That's extremely important with our notation. And then we've got -2 to 1 of 2 dx. Well, using the constant multiple, I can actually pull this -3 out front. X dx, so x cubed. And then I can pull out this 2. And I can pull out this 2 as well. 2 to 1 dx, and then I could evaluate my integration from here. If it is known that the integral from 0 to 8 f of x dx is equal to 10, and the integral from 0 to 5 f of x dx is equal to 5, then find the value of the integral from 5 to 8 f of x dx. So the largest interval is 0 to 8, and we're going to go 0 to 8 f of x dx, and then based on that last property, we know that this can be equal to 0 to 5 plus 8 to 5. And I shouldn't be saying these backwards, but I am. And then we can do some substitution. So we know this one is 10, this one is 5, and this one is the point of the problem, so we're going to rewrite it. And then we find out the solution that the integral from 5 to 8 of f of x dx must be equal to 5. So this is how we find an integration without our calculator, just using the properties. All right, now we have the comparison property of integrals. So if f of x is greater than 0 for the entire interval, then the integral is greater than 0 for the entire interval. If f of x is greater than g of x for the entire interval, then the integral of f of x is greater than the integral of g of x. And then if m and m are constants, such that the function stays between those two boundaries, m and m, then the average value of the function, which is what this notation implies by having that times b minus a, is going to be in between those two values. So let's take a look at f of x equals the square root of 1 plus x squared, and g of x equals the square root of 1 plus x over the interval 0 to 1. The first thing I want to do is graph this function. Okay, I pulled up my graphing calculator, and so we've got insert square root of 1 plus x squared. I need to delete all that extra. And we've got the square root of 1 plus x. Oh, do I need to get rid of that? Yeah, I do. Syntax error. There's a little extra exponent hanging out that I want to remove. Okay, enter. And then go ahead and graph these functions. And then we're specifically looking at the interval 0 to 1. So I'm going to switch my window settings to 0, 1. It doesn't look like I need as wide of a span for y, so I'm going to do 0 to 2 and graph it again. It's really hard to tell, but it looks like the first function, or the second function, is always larger than the first function. So But let's just get a little closer. I'm just going to change my y to be 0 instead of negative and see if I get a better view here. So there's my first function. Yeah, much clearer. The red function is clearly larger. So what we would say, according to the comparison, and this is without calculating any sort of integral or doing any sort of integration, we can be confident to say from 0 to 1 that gx dx is greater than or equal to 0 to 1 f of x dx. All right, this is going to be the end of part 2 of the video notes. In the last part, we're going to take a look at the average value of a function using the definite integral.